Okay. So welcome everyone to the fifth lab session of the deep learning course. And today we're going to be studying about natural language processing, or NLP for short. Um, we've actually done quite a lot in computer vision till now, specifically from the perspective of deep learning. And so let's actually pivot a little bit and look at another very popular domain in deep learning, which is called natural language processing, which, as the name suggests, is related to deep learning methods with how to deal with language and text, speech, audio, stuff like that, right? So let's actually first understand like what natural language processing exactly is. I'll give you a very basic idea about what natural language processing is, but let me just write down something. So natural language processing is actually a very broad field in artificial intelligence, that deals with understanding language. So this includes building models that understand speech, audio, text, etc. So for example, you must have seen Google Translate. It's an AI model, and it somehow knows how to convert a piece of text or speech into another language. Or you say hi Siri, or you say hi Google, hi Alexa, and your phone or your home assistant. And I said hi Google, and my phone lit up just now. Just a second. And so your home or your phone assistant responds to you in an intelligent way, just like my phone did right now. And this is where today's state of the art of NLP actually lies. But there's so much yet to be developed and discovered. It's a very active field of research in AI. So let's actually talk about like some aspirations within this field. Like, what exactly does natural language processing actually try to achieve? um, Natural language processing is not only about identifying language, but also understanding it, right? Currently, NLP is not quite good at that. It's not quite reached there. For example, we still don't know how to build models that actually understand the semantics of a language. Like, just apart from identifying English, we don't know how to build models that understand, let's say, sarcasm, emotions, or slightly misspelled or mistyped words, and so on and so forth. So today's models don't actually understand context of a piece of text really well. Yeah. In fact, there are models now that can generate entire segments of text. And if you just have a very quick glance of them, if you just do a very superficial inspection of them, it just seems that the model generates very sensible text and you give it a very good go ahead. But if you inspect it really closely, you'll find that most of the text doesn't actually make sense. So, which is why even in 2021, as we're going to 2022, most AI chatbots that actually exist still don't work really well. So that's where NLP actually lies. And to be fair, it's actually not that we don't know how to model AI models really well, but it's just that like we humans ourselves don't know how to actually model language on a very broad level. So though I mean, I do expect that in like a few years we'll be able to develop much better modeling methods to understand language. Um, and then there will also be like newer types of models for NLP tasks which we absolutely know nothing about right now. So present models and optimizers just do the job, like very on a very superficial level. But it's possible that NLP techniques will see some major changes in the coming few years. Um, so today we're gonna be looking at some state-of-the-art natural language processing models in AI. We're gonna be building like some standard recurrent neural network models. We're gonna be building LSTMs, right? And we're also gonna be looking at like one really a model that is like one of the most hot topics in natural language processing, and it's actually also going in other domains. It's called the transformer model. And we're also going to be building and training our models, and actually see like how state of the art NLP models are built. So by the way, transformers is actually the model which is used in like those models like GPT-2, GPT-3, BERT, Roberta, and whatever, and whatnot. So it's a slightly code heavy session because we're trying to be having we'll be trying to get a very broad level overview of entire NLP within one session. And so I think that and so I think that it's a very good point to actually introduce you to APIs, different libraries apart from the ones that we already use, like just PyTorch and whatnot. So we're actually going to use some even more high-level APIs, which I think that, and what they essentially do is that they actually save you a lot of time by actually just giving you pre-written code, right? So that's the job of APIs. So we're going to be using libraries like Hugging Face, which is actually one of the most leading libraries in what do you call in NLP, right? One of the best what do you call startups in the NLP space. We're also going to be using for general training methods and for other like some general deep learning stuff. We're going to be using the Fast AI library for everything like data sets and like building like the classes related to data loaders, uh, training methods, optimizers, and whatnot. And I'll actually show you that it's not very different from what we've already built. So ideally, if you want, you can obviously build it on your own as well, using whatever we've already done in the previous sessions. But I think it's a good point to introduce how to use new APIs, high-level APIs, and use it in your task. And as you'll see, it's not very hard. It's not very hard to learn. It just takes some smart work, some smart Google searches to actually get your code ready. All right, so we're going to be starting with this library called Fast AI. It's a very good API that I mean just makes deep learning training just easy, very easy. I'm going to be uh, installing the FastAI library like this. Uh, I would have ideally just written pip install FastAI, but FastAI already exists in Collab, but it's an older version. Like the newer version doesn't exist, which is why I have to write upgrade explicitly. All right, and I'm gonna be storing it in a temporary file because I don't want the entire like the installation process printed out. So I'm gonna do that. Let's do that. And of course, as always, you guys can follow me as I write the code. All right, it's installed. Let's actually import it. So if you go to FastAI, the docs, docs.fast.ai, you'll see, and you go to text, which is what we actually want, and you go to let me see if there are tutorials on this. Text tutorial, yeah, let's see that. And you see the very basic thing that you need to do is that you need to write this line of code, which is that from fastai.text.all import star. Right, I'm going to be doing that. And what it will basically do is that it will give me all the necessary modules I need for training my models using FastAI. Now, a little bit about FastAI. FastAI is actually built on top of PyTorch. So when you import FastAI, you'll automatically be importing like a lot of things like PyTorch, and as well as like some very basic, like the standard libraries like PIL, Matplotlib, NumPy, OS, whatnot. All right, so I've imported that, and that's about it. All right, so let's actually look at some really interesting problems that you can solve using natural language processing models in AI. We're actually going to be starting to build. We're actually going to be building a sequential model. And essentially what it means that I'm going to be actually giving it a prompt, a small 3 or 4 words, and what it will do, and model will automatically generate text over and over again. So it's something like auto generative text model. So this is something very similar that you have on your keyboards nowadays. I think that Swift was like one of the first companies that first introduced this kind of models, where you basically have those suggestive text at the top, right? And that uses AI, of course. Now almost all keyboards use that. that AI-based model. Earlier, it didn't used to be like that. Earlier, they used to use simple like Bayesian models and just simple graph-based models and whatnot. So, what you can do is that if you open your keyboard based on your history of how you use your language, it's going to be constantly predicting the next word. And you don't actually have to type anything. You can just simply keep on pressing on those suggested texts and it will keep on writing those things. So, we're actually going to be trying to build that using AI, using natural language processing. All right. So, for that, I'm going to be using a model called as a recurrent neural network. And it essentially is it actually makes some sense. I mean, it's a neural network, of course. I mean, deep learning uses neural networks. Why is it recurrent? It's because like you're constantly going over a cycle of repeating of generating new and new words, so it kind of makes sense that it's named recurrent neural networks. All right, so we'll look at how we build that models later on, but let's actually just first build our data sets and like just do some general bookkeeping. So I'm going to be downloading some data set. I'm going to be using uh, uh, the API from fast.ai and say that let me actually just build a data set using one of the functions. So there's this function called as untar data. Yeah. And untar data basically will first download the data set using like one of its pre-existing cloud services that FastAI has access to. And it will also unzip all the files and it will just get everything ready for you. So you don't have to unzip, you don't have to download separately. So that's what FastAI does for you. I'm going to be using a data set called as human numbers. So what it does, it actually takes a path, right? A URL from where data can be downloaded, and okay, let's actually see what this URL looks like. URL is equal to this print URL. Well, let's actually see. Right, so this is some like this is an S3 Amazon AWS bucket, and it actually already contains this data file in this zip folder. So it actually downloads it through one of these buckets. And I'm just going to be passing this URL to this untar data function. It's going to get everything ready for me, and it's going to return the path where all this data can be found. Uh, what exactly is human numbers dataset? It's actually nothing but just a very general text dataset. It does not contain any labels. It just basically a text file containing like numbers written in words sequentially. So one ONE and then followed by 2, 3, 4, 5, but written in words up till 10,000, I think. So we'll see what that is. But okay, here it is. All right, so it downloaded it. There's apparently 30,252 bytes or files. I don't know what that means. But what exactly is path? Let me see. Right. So apparently it has saved it in this particular folder. All right, that's good. All right, so let's uh, look at what it actually looks like. So I'm going to be doing path.ls, which is again a FastAI function, which basically enumerates whatever files exist in a particular path, but in Linux style. So ls is actually a Linux function, but they've converted it into a Python function. So it gave me that there is a train.txt file and a valid.txt file. Makes sense. I mean, train file and a text file. And I'm guessing it must be sequential. But anyways, so if we first need to read that text file, it cannot be directly read as strings within the Python file. So I'm going to be writing some code. By the way, what exactly is this? L is again a FastAI. It's a variant of the list. So this is essentially nothing but list. By the way, and you can find all this within what do you call this tutorial file over here. You can go to docs.fast.ai and you can get some tutorials. So let me actually just put this over here. It may seem intimidating at first, like any library actually looks intimidating at first, but as you get more experience, you'll find that like actually getting adapted to any new library is not that difficult. Given that, I mean, they have good tutorials and the documentation is good. So all you need is all you need to do is at that point is that just scroll through the documentation, look at like what exactly is the function, get your job done, and then move on. Like that's all you need to do. So so it may seem intimidating right now for any one of you for whom it does actually seem intimidating. You can just follow me for now mindlessly, and then later on, I actually very strongly recommend you that you go through this notebook again and again, try to understand what exactly each function is doing and why is it so. Try to read the source code if you're interested. Right, always works. Um, Anyways. Standard way to read a text file is this syntax, and this is general Python stuff. So train.txt as f lines plus is equal to L star f dot read lines. Actually see what this is doing. So the width as block in Python is a very memory efficient way to assign uh, something to a variable for a very short period of time. So this is a block, and let's say that as soon as this function gets over, this f, I mean, this is freed from the memory forever because we don't need it anymore. So it's a very good way to, read data sets. So all data sets must be actually read this way, ideally. Store it in whatever variables you need, and then just get rid of the extra memory space that you don't need. Similarly, so for now, I actually don't want to keep this train and texting separate. Uh, because I'll anyways be splitting it into an 80-20 sequentially. So if it's from 0 to 10,000 written sequentially, I'll probably do something like up till 8,000, just break that. 0 to 8,000 will be training and whatnot will be validation. But I don't think that's the case like as originally proposed in the dataset. So I'll first be combining them and then I'll be breaking them down later on. So same thing goes for path slash valid.txt as f lines plus is equal to L star f dot read lines. What exactly is a star? What star does is it basically uh, so okay, I'll give it to you as an assignment. Go check it out on Google if you want to know like what exactly is star args. So the keywords that you'll be actually writing in Google is what does star args mean in Python? Why args? Because these are all arguments, arguments of any function. So or a class. So that's exactly what you're going to be writing in order to know like what exactly this is. It's a very good tool that every Python programmer should know, or any. Oh yeah, it only exists in Python. Anyways, let's actually see what lines will look like at that point. All right, so it's a list containing one followed by an enter. The backslash n is usually enter. 2, 3, 4, 5, and let's actually see what line the final word will be. Yeah, 9,999. So it goes from 1 to 9999. That's the data set. All right. Let's actually so instead of this backslash n, and the problem with backslash n is that when you pass it into a string, it will consider backslash n as characters itself. Let's actually just remove all these backslash n's, and we'll replace it with a very generic separator, like let's say maybe a full stop or something like that. All right, so I'm going to be naming it what do you call a text. I'm gonna be doing space dot join uh, L dot strip. What L dot strip is that it will remove any enters, tabs, spaces, and actually just give you the words as a list, right? So that's it. So for L and lines. So for example, lines contains one and a space followed by an enter, so it will remove anything that's a space, tab, enter, and it will only give you O and E. And that's exactly what I want in this list. And then what I'm going to do is that when I'm going to have 1, 2, 3, 4 without any spaces or anything, I'm just going to be joining them all with this generic separator that I'm defining. And that's going to be it. So let's see what text will look like. So maybe just 100 words will do well. Yeah, so 1 space dot space 2 space dot space 3 until so on and so forth. Anyway, so that's my uh, what do you call the text file that I'm going to be using as input to my language model that I'm going to be building. So let's actually tokenize it. So let's actually talk about like what tokenization actually means in natural language processing. So just like so what essentially I want to build right now is actually I want to build a model that will probably take 1, 2, 3 as the input, and it automatically understands that I have to continue and it will predict like 4 and then 5 and then 6 in words and so on and so forth. So now I of course can't pass 1, 2, 3 as a single string because computers don't understand that it contains 3 different numbers. It will consider it as one. So I need to first break them down into small chunks, right? That will form the very basis of my language. That just like we break down language as into words and words into characters. Similarly, you need to break that down into components that form individual entities have different because they have every word has different meanings. And so if you want if you want the computer to learn the different meanings, you have to first make it understand that these are different entities and they have different meanings. So the very first step is to first break them down into different entities, and these entities are called tokens, and this process is called tokenization. So that's a very basic understanding of what tokenization means. Right now, all I care is about, I'm just going to be breaking down this entire sequence into small parts. And the easiest way to do that is probably like splitting, just finding that wherever there is a space, so any two entities separated by space will constitute as two different, what do you call, two different tokens. So anyways, I'm going to be saying tokens is equal to text dot split. By default, text dot split is actually the function which will separate each token by spaces. So let's actually see what that will look like. Tokens, probably the first line will work. Yeah, so 1 followed by a dot without any spaces, 2 dot, 3 dot, 4, 5. Yeah, so that makes sense. That's going to be the input to my language model. But now you realize that the computer actually doesn't understand the difference. So when I say 1, 2, 3, 4, 5, and then I reach 19, 20, and then 21. So 21 actually consists of two words, 20 and 1. And I want my language model to understand that this is how numbers are constructed, that you first say 20 followed by 1, 2, 3, 4, 5. That's how the English language works. And that's actually what I want my model to understand. But the computer doesn't understand that when you're going to be writing, let's say, yeah. So when you're going to be saying 1 and then 20 and then 1, computer actually thinks that this one and this one are very different entities, which is not acceptable. The computer must understand that the basic construction of the English language actually consists of just that one word, one, and that one is actually repeated many times, rather than computer thinking that, oh well, like, each number is constructed with a completely unique word. So I need to create a vocabulary, a dictionary of words that contains only the unique words, and that's going to be the very basis of my language modeling. So I'm just simply going to be what do you call, building a word that contains I'm going to making a list that only contains the unique words within that model. So this can be actually done using this. Now lists, L is nothing but a list, and lists don't have a function known as unique, but FastAI actually gives us with this function called unique, which will actually just give you um, just the unique words within the entire list, whatever you pass as the input. Okay. This is actually very same to list set tokens. Because set actually returns only the very unique elements, because it's an implementation of something known as a hash map, and hash map makes sure that you get unique results. And then once you convert it into a set, because set is not iterable, it's not, sorry, indexable, you convert it again into a list. So that's exactly what this function is trying to implement. Let's see what vocab is. All right. So by the way, let's see how many words does a token does this text tokens originally have. So this is tokens. Tokens actually consists of 63,095 different words, which actually contain many repeated words like 1, 2, 3, and they're repeated multiple times, like 1, 21, 31, 41. They all contain the letter 1. And so all these combined will actually give you 63,095 different tokens, right? But in essential, there are only 30 different unique words, including this dot. So essentially, there are just 29 unique words that build up the entire numerical set from 1 to 9,999. That's quite interesting. So that's going to be my vocabulary, my dictionary that contains the unique words. And I'm going to tell my language model that this is the very basis. This is the entire universe that concerns you as of now. This is the dictionary that you need to refer to for any word, like, and so if you want one, you can only choose one once and not different times. Anyways, okay. And the next step is actually called numericalization. By the way, these are all very standard steps in natural language processing. Like any natural language processing problem, you will have to follow the steps. Create tokens, create a vocabulary, and numericalize them, and then we'll see what happens. What numericalization is? It's actually very simple. We understand the words 1, 2, 3, 4 written in text, but computers don't understand what you call characters. They only understand numbers. So we need to first convert everything into numbers, so that computers can understand anything. So I'm just gonna go sequentially. I'm gonna assign this as the number 0, this as the number 1, 2, 3, until blah blah blah, blah until 29. So word to index. I'm going to be creating a dictionary that's basically going to be mapping each word to its corresponding numbers in its sequential order, like in whichever order it exists. Let's see what that means. I'm going to be store the numericalized values in in this variable called nums, and it's simply going to be word to idx I for I in tokens. Right, let's say nums. Yeah, so again, we have 60,095 words, and corresponding to these tokens, I now have a numericalized version of them, which is 0, 1, 2, 1, 3, 1, 4. Makes sense, right? I mean, like there was a dot between every two numbers, and so there is this numerical one between every two numbers in the beginning. All right, so we're done with the basic data setup. So now let's actually build our natural language processing model, and we're actually going to be building the recurrent neural network, a very standard recurrent neural network in PyTorch. One more thing. Okay, so we are essentially building a neural network model. You guys know, and I know, that neural network models always work on inputs and outputs. You know, it's a supervised learning problem. A neural network is always a supervised learning problem. Like there are methods that are self-supervised and whatnot, but self-supervised learning is also a supervised learning problem. If you look at it, like it's an unsupervised learning problem that is engineered to be a supervised learning problem. So a neural network is essentially supervised. And so we need to define inputs and outputs for that model. So what do I want my model to do? I want to give my model an input, which is, let's say, 0, 1, 2, and I wanted to predict 1, right? And then I wanted to predict 3, and then I wanted to predict 1, and then 4 and 1 and whatnot. So that is what I want my neural network to do. So what I'm going to do is I'm going to do some clever engineering, and this is actually something known as self-supervised learning. Let's actually see what that is. Self-supervised learning, which what I'm going to do is that I actually initially have an unsupervised learning data set, right? It's just inputs. It does not have any corresponding output explicitly. But let me actually create and engineer a data set out of this unsupervised learning data set that looks like an input-output mapping, and so it will become a supervised learning problem after that. So tell me if it makes sense to you. What if let's say I give the input 0, 1, 2, right? Then I want my model to predict 1, so this is going to be the output for what do you call this corresponding input of 0, 1, 2. But now, because neural networks always expect the model to look like the same way, the input and outputs to look the same way, my second input, to which the output will be this 3, should also look the same way, like in this way. So let's say I'm going to say that 1, 2, 1 is going to be my input, and then 3 is going to be the what do you call output. Similarly, 2, 1, 3 is going to be the input, and the output of the model is going to be 1 again. So that is how I want to model my network. So does that make sense to you? If it doesn't, tell me. I'll explain it again. Right. So I'll tell you now why it's called self-supervised learning, because essentially it's not explicitly supervised because it does not have input and output mappings. But using that whatever data set we had, we actually created outputs from that data set itself. So the model is actually made itself a supervised learning problem on its own. So that's why it's called self-supervised learning. So that's the concept behind self-supervised learning. So self-supervised learning, this is my definition. And you'll find different definitions online, but I think that this usually helps me, and it'll get you past whatever interview you want to get through. So according to me, and this is only my definition, beware. You're at your own discretion, but for your understanding, it's good. It's basically an unsupervised learning problem that has been engineered to be a supervised learning problem. Okay. Why? Why do you want an unsupervised learning problem? Many reasons. It's not always feasible to what do you call label your data sets. And when you're talking about language models, it doesn't make sense to have an output itself. Like you want a model that understands language itself, and so that like the way you provide language to it's like you can provide a huge corpus of Wikipedia text, and you tell your model ideally like I've given you all the information you need to identify whatever patterns you need within the language. So what output do you need? Like you can just ideally you should be able to understand the entire language just by giving enough examples, which is just like give it as much text from Wikipedia, let's say, as possible, and I ask my model to understand language, the English language. And so that is where unsupervised learning comes into play, like especially in natural language processing. But now, why would I want to convert it into a supervised learning problem and not simply use models that actually run on unsupervised learning principles? Is because I want to use neural networks, because we all know that deep learning models work really well, but deep learning problems only work in a supervised learning fashion. And so it's important to engineer it into a supervised learning problem. And so this intersection is called self-supervised learning. Anyways, let me create this data set. What I'm going to do is that I'm going to be creating tokens of 3. So it's so okay. Just copy me for a second. Yeah, so 1.2 will that is the input as a list, and the dot is an output, and then dot 3 dot is the input, and that corresponding output becomes 4. 4.5 is the input, and dot becomes the corresponding output. Of course, we need to first convert them into the corresponding numbers, numericals as well. So we need to what do you call numericalize them as well. We'll do that later on. That's not a problem. Anyways. Uh, so yeah, this will become my input basically. So let me actually just name it as sequences. I'm just going to be giving it a name called sex seqs QS. Then one more thing actually. What do you call deep learning models, especially PyTorch models, don't understand uh, lists. It only understands something known as tensors, which we all know very well. So it's very simple. Let's actually just convert this list into a tensor. It just makes life easier for the deep learning model. So I'm just going to do a tensor. Yeah, by the way, in PyTorch, sorry, in FastAI, you don't have to, because they've already imported torch, and they've already imported tensor from it. So you don't have to write torch.tensor. Tensor works fine. Works fine. You'll see. Oh, there's a mistake. Um, oh, sorry. You can't pass in strings into tensors. So, of course, so not, tokens don't go into the tensors. You'll actually have to pass the corresponding numericalized list. So that's that. Yeah, it works. Let's see what sequences look like. Yeah, tensor 0, 1, 2 gives 1 as the output, tensor 1, 3, 1 gives 4 as the output, 4, 1, 5 gives 1, so and so on and so forth. So that becomes like our data set. Of course, we need to construct a data set out of it. But the good thing about fast AI is that we don't actually have to construct the classes for the dataset and all, because it provides methods in the API to directly take in lists as the input and give you corresponding data sets as well as data loaders. So you'll see how to actually build a data loader directly from lists as the data. Otherwise you would actually have to construct the data set class and then convert that data set class into a data loader and so on. That's actually quite hassle. That's quite a hassle. And so that is where APIs actually make life much easier for everyone. Um, all right, so let's say DLs is going to be data loaders. So data loader is a PyTorch class. Data loaders is a FastAI class, which is actually just a class that contains both the training and the validation data set, data loaders. And by the way, we have actually constructed this in one of the labs. I don't remember which. I think lab 2 or lab 3. So you guys can check it out if you want to. Um, and I'm going to be using one of its wrapper methods, which is called from datasets. And this is built using something known as delegates within Python. So if you want, you can have a look at what delegates means. Actually, hello world. And that's actually so what it does is that you actually have to give the training and the validation data set separately. So I need to first define like where exactly I want to cut the model, the data set. So as you talked about, we're just going to do an 80-20 split. So I'm going to be defining it within something known as uh, cut. And so I'm going to be passing in the index, which corresponds to, let's say, 80% of the data set. So that's going to be this. Yeah. And so this becomes sequences cut. So that's 80% of data set. That becomes the training set, followed by the validation set. Right. The batch size is a standard PyTorch API and it's actually built in within the FastAI API as well. I'm going to say 64 maybe. 64 is a good number set. And shuffle equals false. Now, very important, shuffle should always be false within language models, because you want your model to understand the sequentiality within the data. Like after 1 comes 2, 3, you can't shuffle language models. It doesn't work. Like your model will never work. So always make sure. Right. By the way, let's see what DLs exactly gives us. DLs is nothing but anyways, we'll look at what DLs is. Anyways, data loaders are built. So my data is all set up. So now all we need to do is actually build a recurrent neural network. Let's actually look at what recurrent neural networks exactly is. All right. So let me actually tell you what recurrent neural networks essentially is, and let's actually go. We'll go down images and probably, if I get some good representation, I'll tell you what exactly it looks like. Okay, this is actually pretty good. And let's actually only look at this left part over here. Oh, this is good. Is there a GIF that I can find? No. Oh yeah, this is good. This is good. This is good. Um, okay, so do you see that this moving GIF over here? So this red thing, red dot over here is nothing but the input. You give some input, and this is the final output, this black one. But in between, is this constantly, there is one, let's say, entity, that's a small neural network, or maybe one single linear layer within the model, or let's say even one neuron. Can be anything, by the way. And what exactly happens is that when you give input 0, 1, 2, the that linear model that we just talked about, or this small blue whatever computational unit this will give the output 1. But that 1, which was actually the output of the model, also has to be fed again into the model, right? Uh, uh, so so now what we're going to do is that 0, 1, 2, we're going to throw out the 0 value, and we're going to take 1, 2. And then we're going to take the 1, which was the output of the recurrent neural network, and we're going to feed that into the model. And that, again, that computational model is going to predict something, So this process keeps on going on until you reach some final state. So that is why it's a constant loop, and hence it's called a recurrent neural network. So does that make sense to you guys? It's actually quite interesting. If it didn't,
Yes.
I'll explain it again to anyone.
Excuse me.
Yeah.
Like, how is it different from a normal neural network? Like, we are just passing the changed input again with the first output that came. Like, so, how is it different?
From a normal neural network? Okay, so here is a good image of a normal neural network, by the way. So the normal neural network, first of all, I'll talk about two differences probably. The first difference is that a normal neural network contains of many layers, many different layers. So each input actually goes through different computational units. So it'll first go through the first hidden layer, which is this 4-unit linear layer over here, and then it'll go through this second linear layer, which is this 3-unit, and then probably go through the same things. A recurrent neural network model is probably people found out that it's not a good idea to, you don't need to have different computational units again and again. You can have this 4-unit linear layer, and then whatever is the output of this 4 linear unit layer, you can again feed it into the same 4-unit linear layer. So this is exactly what's happening over here. So that is why it's called a recurrent neural network. It makes sense. I'll tell you why it makes sense, because whatever input number 1, right? Input number 1. So all the knowledge about the language is stored within some recurrent neural network. And so let's say that you can, whatever information you're passing for the first input through that linear layer. So the same, okay, let me rephrase. So when you pass this 0, 1, 2 into this blue computation unit, which can actually be either 1 layer or 2 layers, or 3 layers or whatever, some computation. It can be a whole neural network, it can be a single linear layer. So there is some input, and you expect the model to do some transformation which corresponds to its knowledge about language in general, and it's going to give some output. But now, because I want my model to continuously predict the answer, I'm actually not going to be passing any new input to the model. I'm actually going to take that output and again feed it through the same neural network model or the same blue computational model to predict the next input. So difference between a normal neural network and the recurrent neural network is that a normal neural network will actually take different instances of inputs and outputs at each point, whereas a recurrent neural network will actually take the same. It will actually take its own output and convert it into its input again to actually make the next set of inputs. So does that
So,
make
like,
sense?
can we use the normal neural network as well for the problem? Like, is it possible?
Yeah.
Uh,
No. By the way, these are. It's not entirely different from a normal neural network. The only difference is the way we engineer it. Uh, let's actually talk about it. You'll see that this is essentially just it will actually form a neural network model. Uh, but in a normal neural network model, you always have different instances of x's and y's. There is always a ground truth, right? So let's say you pass an image, this is a cat. You always have some ground truth. And the next instance will actually not be a derivative of the first output of the model. It's actually just going to be like a second image and a second label, and a third image and a third label, right? Now, the only difference that I want to point out right now is that my problem is different. I actually want to build a text generator that's actually going to, I'm just going to be passing in the very first three words, and I'm not going to pass it anything else. And I expect it to give me like 10,000, a paragraph of 10,000 words, let's say. So, what I'm going to do is so my input is only going to be 0, 1, 2, right? And it's going to give me output 1. Like it may be right, it may be wrong, right? So, but what I'm going to do is that 1 again is going to be the input to my model. So this 1, 2, and this is the prediction of the model, and it's going to give me another output, and that again is going to be my input. So because of that, all I'm doing is that I'm actually just feeding the output as the input again into the model, into the neural network model. So that's the entire difference between a recurrent neural network and a normal neural network. Is that I actually don't have separate instances of inputs and outputs. It's not a supervised learning problem. It's a self-supervised learning problem, which actually requires me to loop in the output as the input. So input becomes output. That output again becomes input, and you get some other prediction. Then that again is fed as the input. So that's the entire difference between recurrent neural network and normal neural network. Have I answered your question, or have I missed anything? Are you sure? Okay. Let's build it, and we'll come back to this question later on. Okay. Let me build this model. Oh, okay. Let's actually look at it this way. This is actually the same GIF, this exact same thing, but actually represented in an expanded form. So now it will actually look like a normal neural network to you. This is the input, this red input. It goes through that blue computational unit. It can be a linear layer, it can be an entire neural network model. It gives me some output, and that output is going to be sorry. So what it's going to do is that I'm going to pass it some input, and I'm going to be training it, like based on whatever metrics I use. So I'm actually going to be trying to tell my model that this is your target output, and what you did was that this, and based on the error, you're going to try to converge using gradient descent. So it's going to come to a new state, which is this second blue ball. And then what I'm going to do is that I'm going to pass in the prediction from the last case as the input to the model again. Oh, that's the prediction case actually. So what I'm going to do is that now that I've trained my model using the first instance, I'm going to go to my original data set, and I'm going to say that let's actually take 1 to 1 as the input and 3 as the output. Again, that's what you would do in a normal neural network. You're going to pass in through the network, you're going to train it, and you're gonna tell that the model was supposed to predict 3, but it predicted 4. And so I'm going to do a normal cross entropy loss function to actually converge that neural network model, and it's going to come to its third state over here. The model is probably slightly better, and then I'm going to say that okay, you're now in a better state. Okay, now I'm going to give you an input 1, 3, 1, and the model is going to say that what was supposed to be the output? 4 was supposed to be output, and let's say the model actually proposes 4, so that's good. So the model will actually again update to come to the next state. So that's exactly what a recurrent neural network is. It's basically uh, uh, it's just a normal neural network model if you look at it this way. But now what I'm going to do is that finally, when I'm going to be building predictions, what I'm going to do is that I'm actually going to be passing just that one single input from here, 0, 1, 2. And then I'm essentially going to be saying that whatever is your output now is actually going to become your input again. That is actually not possible in normal neural network models unless you engineer it in that particular way. So that exactly is what uh, you mean by recurrent neural network model. So, anyways, let's build that model and it'll probably become clearer. Plus RNN1. Okay. Passing it nn.module, of course, as always. You're gonna do a def init self vocab size because we're actually going to be talking about some really important concepts over here, and something known as n hidden, and we'll see what that is. So always initialize what do you call the nn.module, very important. All right, so next I'm gonna do something known as self.input I underscore h is equal to nn dot embedding gap size and hidden. I'll actually talk about what this embedding layer is, and you're going to be using it very often for NLP problems. But for that, let's actually just build the entire architecture, and I'm just going to do a small 2-layer neural network as the blue computational unit that you saw just now. Self dot h is equal to nn dot linear and hidden. Yeah, that works well. I mean, I can probably take in 2 different inputs, but it doesn't really matter. And then self dot ho. By the way, this is h hidden. This represents input to hidden. This represents hidden to hidden, and this represents hidden to output. And this is again another nn dot linear layer. Hidden, and then vocab size. So of course, the input and the output should be of the same size because uh, uh, the input and the output are essentially nothing but of the same type, right? They're just words, and these also are words. So that's exactly what I'm trying to do. Anyways, what exactly is this embedding layer? Let's talk about that. So all these different tokens that we've generated over here. The problem with tokens in natural language processing is that they're discrete in nature. This is only just a mathematical nuisance that you have to understand in general. Tokens are discrete in nature, right? Because, of course, they're separate entities. But uh, deep learning models, and so whenever you're representing, let's say, uh, uh, let's say 21, the way that you actually represent 21 in discrete form, in token form, is actually something known as a one hot encoded vector. So it basically is, let's say that there are 30 unique words. So I'm going to be creating a vector of, let's say, 30 different zeros, right? And wherever there is, let's say 20 comes at, let's say, this position, so this will become 1. And then there is 21, so this token will become 1. And so this becomes the input to the model, right? But the problem with this is that this vector is way too sparse to do any sort of computation. Because there is literally, like, most of it is zeros, and so you know that 0 multiplied by anything will be 0. So this is actually not going to contribute anything to my model. So what you can actually do is that corresponding to each of these numbers, over here, you can actually construct another vector of some shape, and that's going to be and that is actually going to contain a lot of information. So literally each one of these positions has a corresponding vector of them, and that is going to be containing a lot of information. Let's say some vector. Anyways, so whenever you do so many zeros, and let's say there is just this single one over here and single one over here, this is basically be corresponding to vector 1 followed by vector 1, 2, 3, let's say 10, whatever. Vector 10. Yeah. And so these vectors corresponding to this particular position over here and this particular position is actually known as embedding. It actually has two purposes. First purpose is to actually expand the information within this very sparse one hot encoded matrix, because in a new one hot encoded matrix, the information contained uh, within that one single unit is very less, and secondly, it actually helps make the model fully differentiable, right? Because ideally, these tokens are discrete in nature. Anyways, if that is confusing to you, it'll actually be clear through an example. By the way, I understand that all these things will be confusing at first. It's impossible to learn it in one go, right? Uh, but essentially, nn.embedding is basically a two-dimensional matrix, right? And so when you multiply that one hot encoded matrix with that two-dimensional matrix, what will happen is that all the zeros will cancel out, and so only the vectors, only the rows corresponding to let's say wherever there is a 1 will actually remain and get added up, and that is going to create a vector that contains enough information to represent those two ones that corresponded to 21. So now 21, when I give it as an input, will actually be a new vector of size and hidden, right? So the input of size, vocab size, so let's say 1, which is the number of this is how a one hot encoded vector will look like. Actually, can I draw it somewhere? Yeah. Let me just erase everything. So I think this is actually quite important for everyone to understand. So I had a vocabulary size of 30, right? So this is 30 cross 1. Anyways, so the way I represent 21 will be that, let's say this is 1 was over here, followed by a dot, followed by 2, 3, 4. Anyways, so I'm going to say that there is a 1. Is there a dot within this 21? No. Is there a 2? Yes. But not 20. I want 21. So this is not 2, 1. This is 21. There is no 2. Blah, 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 blah. 20. Yes, there is a 20. Is there 30? 40? No, no, no. Anyways, so this is essentially going to be a 30 by 1 n hot encoded matrix, in which only 2 elements are going to be 1 and the rest are going to be 0. Now, because most of them it is a 0, it does not hold enough information to pass into my neural network. So what I'm going to do is I'm going to create a, let's say, two-dimensional matrix that contains that is of the shape, let's say 30, 64, or any whatever number of features you want, right? So 30 will be the rows, 64 will be the columns. So and it's fully learnable, by the way, by using gradient descent. So anyways, blah, 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 blah. Now I'm doing this transpose multiplied by this, and essentially I'm going to get a matrix of 1:64. So now this 21 gave rise to this one row which contains 64 different feature values, which is probably enough to get a good idea about pass enough information to my neural network model. So that's exactly the purpose of this NN dot embedding, and it's fully differentiable, by the way. You can actually backpropagate through it very well. So that's the purpose as well. And once I get those features are going to be passed into the neural network model. The neural network model is going to produce some output, and that output is again going to go back into my model. So now let's actually see how this model actually works. So for that, I'm going to be defining the def forward. Self x and let's actually represent the input features as hidden units, because I've written n hidden over here anyways. So h is equal to 0 at first. Makes sense. And then I'm going to do, what I'm going to do is that, see, let's actually build a variant of this. So this, I mean, just on a very top level overview, I actually told you like what a one hot encoded matrix, like what exactly is our approach. But a more computationally efficient method is to actually use just a very strict one hot encoded matrix, and that essentially means that at once there will be only one, and the rest will be zeros. So there cannot be two ones, there cannot be three ones, and so on and so forth. Can I increase the size of my eraser? Okay, never mind.
You can clear the frame from top left corner.
Oh, okay. Thanks. Okay. So when I say 21, I'm going to be dividing into 20 and then 1, by the way. And my input actually contains of 3 tokens, right? So it's 0, 1, 2. So 0, 1, 2 basically means that first we'll have 0, the 0th element as 1 and the remaining zeros, followed by the first element. Sorry, this is an arrow. The first element is a 0, second element is a 1, and the rest are zeros. The second index is 1 and the rest are zeros. And this is my input, and I expect the output to be 1. So when I give this as the input sequentially, I expect my model to give this as the input. So 0, 1, 0, 0, 0, 0, right? Why am I not going with 21 directly? Like ideally, this is not wrong. Like the model will still work if I still do 1, 0, 0, 0, 1, right? It will still work. But the problem with that is that that model now does not know the difference between 20 and 1 separate entities, and it considers 21 to be a completely different entity. Like this is different. This is actually different from 20 and 1 separate as separate entities. And so the reason I'm actually doing this is because we discussed before that I want my recurrent neural network to understand that 21 is actually constructed from two basic elements, 20 and 1. So it's important to represent them separately rather than as one entity, right? Very basic thing. So what I'm going to do is that I'm going to be first passing this. I'm going to be passing this into my recurrent neural network model, right? Into my blue model. This blue is going to come back. And what I'm going to do is that I'm going to be feeding the next input, which is this one, plus whatever this became after feeding it to the recurrent neural network model, into that blue computational model. So essentially what this becomes is that this red, so at step number 0, at step number 1, okay, let's say, I passed 20 as the input, whatever one hot encoded matrix there was. I passed it through that blue layer and it became something. And now I'm going to be passing in 1 plus whatever that 20 became, and I'm going to add the, and whatever that is going to become, I'm going to add it to, let's say, 2, sorry, 21 and whatever follows after that, let's say a dot. And so that is how it becomes a recurrent neural network model. And so whatever comes after that very third token becomes my output for the model. That is how recurrent neural network models work. So is that clear in some way? Let's actually code it up for you. So for I in range 3, I don't want to hard code it for now, but for now it works. So h is equal to h plus self dot I h x comma I, which is, and of course after each linear layer there's a relu as always. There's a relu self dot h h h, and finally I'm going to do return self dot h o h. Yeah. So what essentially I'm doing is that for each of those 3 elements, first I'm going to be passing it through a recurrent neural network model. Initially h is 0, so we can ignore this. So it goes through that embedding layer. Then it goes to this HH, which is nothing but a linear layer, followed by a ReLU. And then it again goes to this output layer. And now it becomes some state, right? So sorry, this output layer can wait for some time. But what essentially I'm doing is that this layer itself is the blue computational unit over here. This blue computational unit over here. And what I'm going to do is that I'm going to be taking whatever output came from the previous input, and I'm going to be adding it to the new input. So when this is passed through the hidden layer, output is the hidden layer. And I'm going to be taking this and I'm going to be adding this to this, and I'm going to be passing this to the hidden layer, right? So I'm basically expanding the middlemost layer. So that is why, and it's actually not two different things. They're actually the same layer. And that finally becomes the, and that is then passed into the final output layer and you get the output. So now it will become clear to you that what essentially I'm doing is, and so this is a normal neural network model, Richard. And what essentially I'm doing is that I'm doing 2 changes. First of all, this layer and this layer, these 2 hidden layers are not separate layers. They're actually exactly the same linear layer, and you can actually, ideally you can make them 2 layers, and those 2 layers keep on repeating each and time, 3 layers keep on repeating each every time. But for simplicity, they're just the same exact time. And then the output from the previous input is actually also the part of the what do you call the present input. So this becomes something like this. I mean, like when I saw that it's actually looping like this, what exactly is happening is that you can actually expand it, and you can see that there's actually the input from the previous actually goes again to the same layer, and that again goes to the same layer. Each time you get some output, and that output you're going to be applying the loss function to that. But essentially, this is exactly the difference between a recurrent neural network model and the normal neural network model. Is it slightly more clearer to you now? All right, that's good. Let's actually see if this works. Yeah. So x comma y is equal to next iter. By the way, dl's 0. I'm not exactly sure how dl's works. Oh, fuck, it's a list. Anyways, yeah, okay. So DLs is nothing but a list of 2 different items. The first one is the training data loader, and the second one is the valid data loader. So when I say 0, I'm saying the training data loader. And I'm just going to say that xy is equal to this. Let's see what x dot shape is. I'm going to be passing this x through the model. So untrained model. So model is equal to RNN, vocab sizes at len, vocab, and then n hidden is going to be, so what's my vocab size? 30, right? So 64 is probably a good size. Um, model x dot shape. Let's see if it works. Yeah, it works well. Uh, Yeah, so there's going to be 64 members of batch size, and finally I have 30, which is again a one hot encoded matrix. And so whichever is going to be the maximum, whichever is going to be maximum argument, I'm going to say that the model is actually predicted that. It's just standard how we used to do the previous iterations. All right, so let's actually build the model. And what we're going to do is we're going to use this function known as learner, which is actually very similar to the learner that we use, which is nothing but a class which contains a training cycle that for epoch and epochs x comma y is equal to next dot iter dot train dl, pass the x through the model, pass it through the loss function, optimizer dot step, optimizer dot backwards, sorry, loss dot backward, optimizer dot step, optimizer dot zero grad. Then for valid for x comma y and valid dl, same things. If you want to do accuracy, put it into accuracy and whatnot. So you can pass in the dls, you can pass in the model, you can pass in you need to pass in the loss function, by the way, and it's going to be cross entropy loss, because this is because if the output is 3 and the model predicts 4, it's not that it's like it's better than if the output was 3 and the model predicted 5. So it's not, you can't do a mean square error loss. It's actually just a classification problem at that point. So cross entropy loss, you need to use that. And I don't need any metrics, so it actually also gives me an option to put in metrics. But I'm not going to be doing that because, as you'll see, that accuracy is actually not a good measure when it comes to recurrent neural network models. But okay, for the sake, let's actually just put it anyways. This is, by the way, just the API, and we can learn it 10 times. Learn.fit, let's say 3 epochs, and then 1 e neg 3 as the learning rate. This is the LR. This is epochs. So it's training. You see the accuracy is something like 46%, 49, 50%, let's say. So 50% of the times it gets it right, which is actually a good thing. It's not extremely bad. You might say that we've actually seen models which have 95% accuracy, 99% accuracy, and so on. So, like, why are you saying that this is good accuracy? I'll tell you why. For any language model, and as you'll see, this becomes a problem later on. A model does not necessarily have to predict, can actually still make sense without actually predicting the correct word. So 20, let's say the model predicted 22, 22 is still a valid like answer, rather, and but like in a very strict mathematical form, it may be wrong for the computer because it was supposed to predict 21, but if it predicts 22, it's not entirely wrong. Now, like, to put it into perspective, let's say that the model, let's say I actually put in a normal text rather than these numbers, and the model was supposed to predict that the answer to the universe is 42. But let's say the model somehow predicts, given all its data, that the answer to all the questions in this universe is 42. Now, for the model, that's wrong, but we know that it's not entirely wrong. It still makes a lot of sense, and that itself is commendable for a recurrent neural network model. So accuracy is actually not a very good metric when it comes to recurrent neural network models. Rather than that, we'll actually see that some other metrics like perplexity, um, maybe a better metric for such generative tasks. And you can search for it in your own time. So that's a very basic recurrent neural network model. Let's actually see that why this 50% accuracy is not entirely bad. So by the way, uh, let's actually look at the most commonly occurring word within. Okay, let's say that the model was completely random. So a random probability would look something like 0.033%, so 3% or so, and so it's way better than random. Of course, it's 50%. But a good exercise to be, let's say the model only predicted the most commonly occurring word, which I think is the word thousand, because the thousand occurred so many times, right? Like 1001, 1002, 1003, 1004, up to 9999. So I think thousand, the word thousand occurs the most common. Itself, like I know for a fact, occurs only about 15% of the times. Yeah, 15 point something something. So even if the model only predicted the word thousand and it had a very good chance of being a good model, this model is doing way better than that. So yeah, you need to give kudos to that. I'm actually going to be um, doing a few small changes over here. Uh, and this is only to make this model computationally slightly more efficient, right? And what I'm going to do is that here's the problem that happens with recurrent neural network, sorry, with PyTorch in general, is that it actually keeps track of each and every single uh, each and every single value in its computational graph before you do torch.zero grad, right? We already discussed in that. So even though with each new input you're doing h is equal to zero, you should actually the PyTorch is still gonna keep track of all the things that happened before h is equal to zero, and that is not acceptable to us. It just consumes a lot of memory, and so this is gonna become a problem. What do you call, when you make bigger and bigger recurrent neural network models? So what I'm gonna do is that I'm gonna be doing something known as self dot. Uh, so I'm gonna be storing this value in a separate variable first of all. Right? Uh, by the way, let me actually just do self.h over here. Yeah. Self.h, self.h. Um, and then what I'm going to do is that I'm going to do self.h is equal to self.h.detach. So I'm going to be detaching it from the computational graph. And now I'm going to be returning the out value. So now what happens that after I finish one iteration, it's going to simply remove it from the computational graph, which is it's just going to increase my accuracy. Oops, has no attribute h where h. Which line? Oh, okay. Sorry, yeah, I didn't initialize it. Let me initialize this. Self.h is equal to zero. I hope this works. Yeah, it works. This computationally is like, oh, there is some error. Size of tensor A must match the size of tensor B. Uh, oh, oh. Because I'm detaching it, I don't need this anymore. Self.h plus self.I.
Can you explain like the line self dot h equals to self dot h plus self dot input of h, like input I of h, that we are adding the output of the layer to h, and h is supposed to be uh, a number, right? Like, or
It's supposed to be a vector, not
vector.
a feature vector of 64 values or whatever.
Okay.
I'll tell you why. So, sorry, who was this?
So, why
Which,
have we initialized it to 0? I think that might be a problem.
oh no, simple broadcasting. So that will work. That is not a problem. I'm like 0 plus a vector of some size will give you that vector of the same size. That's just general Python.
Acha, okay, okay, okay.
But are you confused about like why we add them in the first place?
No, I was confused, like, why are we adding it to a number? Like, I remember the part where you had explained, like, we are using the previous output and then we are adding it to the input for the next part.
Right. But no, I mean that is fine. I think there's a mistake with the way I uh, created my data set. Let me actually just oh, they go to the original thing. Um, this works, right? Yeah, this works perfectly. Uh, if I create self dot h is equal to 0, then I do a self dot h is equal to self dot h I h x I comma I self dot h is equal to vector hello self dot h h self dot h right out is equal to self dot h o self dot h self dot h equal to self dot h dot detach uh, turn out. What's the problem? I don't understand. 47 size of tensor A 64 must match tensor B at non-singleton dimension 0. Oh, I'm pretty sure
H
I'm
is coming as a 47 length vector. Uh,
and it's at dimension 0, which means I'm probably doing yeah, I'll just spend 1 or 2 minutes more. If it doesn't come, then I'll think over this like in the coming 1 hour, and I'll tell it to you on the group. Ideally, it should work, right? I mean, we're not doing any difference. So if you guys find anything, just let me know. Anyways, for now, I'll just let it be. Anyways, all right. All right, so that's our recurrent neural network model. Uh, you can actually do one thing, which is uh, what you can do is that you can actually expand this small computational unit over here, which was just this one linear layer over here. I can actually expand this into a whole set of linear layers, right? So you're now increasing the complexity of the model, and the model can potentially, work better on. So it can essentially be like multiple linear layers, and that itself will keep on repeating multiple times. So that itself is given in PyTorch as RNNs itself. So um, um, I probably don't need this now. Okay, instead of this hidden layer, what I'm going to do is that I can probably do. Okay, I'm not sure if it makes a mistake. I'll let you know, but let's just give it a shot anyway. So nn.rnn is a function, and that's going to take, of course, n hidden as input, n hidden as output. Anyway, yeah, uh, and then what does it take? It's actually an argument which is known as batch first. I'm going to be setting it as true. Um, and I actually just found this on the PyTorch API. Essentially, what it does is that it. Uh, mm, okay, let's just see. So there's batch first. If true, then the input and output answers are provided as batch sequence feature instead of sequence batch feature. Note that this does not apply to hidden or solid states. See, so which makes sense because the batch is always in the very first position as far as we know. In some, you might have seen in TensorFlow and all, they do it inverse many a times. So that is why this option actually exists. But and it actually has some advantage in other cases, but not for us. Output layer is actually of the same size, and self.h again has to be. So let's just initialize it as zeros. Let's actually try this. Instead of just initializing it, we can probably just initialize it as let's say, and I'm going to be passing it another input over here known as n layers. Uh, why n layers comes first? So by the way, yes, comma n comma hidden is just general size. But then I need a separate self.h for each of the layers within the recurrent neural network model because each of them are going to have different outputs. So forward is just going to become res comma h is equal to self dot rnn. Oh, by the way, this is just API. I mean, like the API already handles all those x's values and all. So self.h over here, self.h is equal to self h.detach. Return self.h comma o. Yes, right. Uh, let's see if that works. Yeah. You see that there is some improvement in accuracy, slight accuracy, and if you train it for longer, you'll probably get better. So probably fit it for like 10 or 15 different models, and so on and so forth. That helps. That helps. Um, Let's actually talk about why the model only performs till 50% accuracy. Why cannot it go like the way we've seen? By the way, state of the art models, there are like transform models which actually can perform this task up to like 95%, 96% accuracy, like even 99% accuracy, like perfect. You can't actually tell the difference between a human and that. Like that's where the state of the art currently is. So why do like these vanilla recurrent neural network only perform till 99, 50% accuracy, let's say? So and the reason that is because it actually faces a problem known as okay. On a side note, oh shit, that was sorry, that was the previous one itself. Like we hadn't trained it completely, so I'm not exactly sure if it'll still work. Let's see, just a second. Um, let's put two maybe. BS is not defined. Did I write BS anywhere? Oh, BS is 64. Yeah, BS is 64. Let's see. Expected hidden size of 1 comma 2 comma that, but received. Anyways, you get the basic idea. I'll make sure to get you like what exactly was going wrong, and I'll share it on the group as well. Anyways, let's stop at this point with recurrent neural network models. Let's get ahead with other things. But you get the idea. This is what recurrent neural networks are. If we had some time and we would have debug the issue, but I'll make sure to do that and let you know. Anyways, so why do recurrent neural network models only perform at this something like 50% accuracy? It's because it actually suffers from a problem known as exploding or vanishing gradients. Just a second. The reason that is because a recurrent neural network model basically takes the output from the previous layer and inputs it into the next layer. So let me actually show you what happens with that. You know that the output itself has some sort of variance, has some mean and some variance. And so what exactly happens is that let's say that the variance, okay, let's say the mean is slightly more than one, right? 1.000, let's say. It's a very small number, very slightly more than, let's say, the traditional one. And now, since I'm multiplying it by itself, sorry, I'm actually increasing it. So let's say that the weight increases it by this factor, by 1.0001 factor. What I meant was whatever input there is, and the input is again fed into the same system. So let's say that the weights, the transformation that is wx plus b, increases the mean by let's say this much factor, And so when you're going to be passing it two times, it's going to be this. Let's say you have a recurrent neural network model that has 20 layers. You're going to be passing it through this. Nowadays you have 150 models. Let's say it becomes this. Actually, this becomes difficult to understand. But okay, for 150, and now let's say I increase it by 500 layers, which is very much. Nowadays, by the way, you use thousands of layers. So now you suddenly increase it by 144 times, 1000 layers. 1024 is a very standard, by the way. Let's do that. 26,000 times the original value, 2048. And so you see, like, this is how gradients explode. And now let's say, let me make this just 0.99. Now suddenly becomes like almost equal to zero. So like that's the entire problem with recurrent neural network models. So let's actually look at something known as LSTMs, now which actually somehow solves that problem. LSTMs were actually introduced back in 1997 by Jürgen Schmidhuber, whose profile picture is actually the WhatsApp DP group of the informal group of this deep learning course. So that guy is Jürgen Schmidhuber, by the way. And in this architecture, there are not one, but there are actually two different hidden states. So over here, we just defined one hidden state, right? This self.hh. There are actually two different hidden states. Let me actually just show this over here. Yeah, when I Wikipedia page, and this is the original architecture that they had proposed, by the way. And so actually there are two hidden states. We'll actually talk about what they are. Um, Now, in the previous traditional RNN that we saw, the hidden state is actually the output of the RNN on the previous time step, right? So the hidden state is actually then responsible for two things. It should have the right information for the output layer to predict the correct next token. And then it also should retain memory of everything that had happened in the sentence. Like consider, for example, the sentences, Henry has a dog and he likes his dog very much. And like another sentence, let's say Sophie has a dog and she likes a dog very much. So it's very clear that the RNN needs to remember the name at the beginning of each sentence to be able to predict the like he or she or his or her part of the sentence, right? And let's say that it comes really later into the sentence, it becomes extremely difficult for the model, for the traditional recurrent neural network model to keep track of that because of that exploding gradients, vanishing gradients problem. So in practice, it has been seen that RNNs are actually really bad at retaining memory, especially like long distance memories. And so this amazing paper from 1997 called the Lstms by Jürgen Schmidhuber actually solved that problem. It's actually dead now. No one uses it anymore, but it's actually really it was a wonderful paper. It's an example of some wonderful engineering, you know. Um, so in our input, this is the input that would go traditionally in our recurrent neural networks as well. This is XT. So it enters on the left with the previous hidden layer HT minus one, which happened in our previous case as well, which was nothing like we used to add them together, right? The activation from the previous time step as well as the current input. So this happens over here as well. So now there is something known as a cell state, and we look at what that is. So instead of just one hidden state, there are actually two hidden states. One is known as the normal hidden state, and one is known as a self state. And these are nothing but like you do some mathematical computation, which you see over here. There is sigmoid over here, tan h, multiplication, addition, tan h, sigmoid, and you get two different values. That's it. That's LSTMs, and I don't know how. I've not actually read the paper, but I don't know how they came up with this conclusion. But it works. It works well. It's amazing. Uh, so I'm not going to be defining what we're going to be defining what tan h is, but anyways, uh, let's go. So let's actually start actually coding up this thing. I'm actually thinking if you can copy this image over here. I'm not sure. Oh, we can. Okay. Anyways, let's actually start building this LSTM cell, and it's again going to be a child of the nn module. Standard def init. It's going to have um, okay, let's actually understand this architecture well. Like first of all, I think that's important. So these four orange boxes, they represent four layers within our NLP model, right? So it can be as simple as just these what do you call sigmoid functions, or they can be actually neural networks on their own. Like if you want to expand this LSTM into whatever you want it to be. Uh, and the thing is that the final activation layer actually has to be sigmoid or tanh or anything. So what they've represented over here is just that one single neuron followed by an activation layer, or it can be a linear layer, it can be a neural network, and so on. All right. We're going to be actually using a linear layer rather than a single single computational node. These green circles here are element-wise operations. So what goes out on the right is the new hidden state HT, and the new cell state CT ready for our next input. So the new hidden state is called as output, which is why the arrow splits into two. So this is the output which you can use, and it again is fed into this again into this thing again HT minus one for the next cell anyways. um, so first, the arrows for input and old hidden state are joined together. In the RNN we wrote earlier in this chapter, we were adding them together, but in LSTMs we actually just stack them as one big tensor. So this means that the dimension of our embedding layer can be different than the dimension of our hidden state. In so now if we call those as so the dimension corresponding to this as n in and this as n hidden. So the arrow at the bottom is of size. I mean, this big lane will have, so the embedding is going to have the size of n in plus n hidden. So thus all the neural network models are linear layers with n in plus n hidden embedding layers and n hidden as the output. So that's going to be the linear transformation. First, the arrow for okay. Okay, so what's next? Let's see. All right. So now these four different orange boxes have different names, given in the paper itself. Let's go from left to right. So this is called the forget gate. Its job is to forget whatever is not relevant. So since it's a linear layer followed by a sigmoid, its output will be considered consist of scalars between 0 and 1, because we all know sigmoid basically scales it from 0 and 1. So you multiply this result by a cell state to determine which information to keep and which information to throw away. So values which are closer to 0 are discarded, values which are closer to 1 are kept. So that's the purpose of the forget gate. So this gives the LSTM the ability to forget things about, in the long term state, like anything that becomes extremely old, you don't need it, just throw it away. Anyways, second gate is called the input gate, right? It works with the third gate, which really doesn't have a name, but sometimes it's called the cell gate. You'll see in some papers. So what it's going to do is that they're going to be multiplied, and that is actually added to this cell state. And so the purpose of the second and the third gate is to update the cell state. And cell state is what we traditionally is basically like whatever information is carried on from the previous layers, basically. So for instance, um, we may see a new gender pronoun, in which case we'll need to replace the information about gender that the forget gate removed already. So similar to the forget gate, the input gate decides which element of the cell stays to update and not. So the third gate determines those update values in the range of -1 to 1 because of tanh function. The result is then added to the cell state. So that is essentially the function of this second and third gate. And the last gate is called the output gate, and it determines which information from the cell state goes to generate the output. So the cell state goes through a tanh before being combined with the sigmoid, and the result is a new hidden state. That's it. Let's actually start writing this code, and we'll probably stop after that, and let's see if we'll continue next time with transform models. Uh, let's see. Anyways, so I'm gonna have the size of the input layer and the hidden layer. self dot forget. So I'm going to be coding the 4 linear layers that I have over here. This is called the forget gate, input gate. This doesn't have a name, but we call it cell gate and output gate. And these are just linear layers, by the way. So all of them, by the way, have an input size of ni plus nh, which is nothing but the embedding size corresponding to xt and ht, which needs to be concatenated, stacked together rather. And the output is going to be the hidden state. That's it. So is equal to linear ni plus nh h. I'm just going to copy this. I'm just going to be copy pasting this. So self dot input gate is equal to this. So self dot cell gate is self dot output gate equal to this. Forward. Let's see. It's going to take in self input and it's going to take the state. This is basically, by the way, it takes an xt as well as ht minus 1, basically. So h and cr is going to be the state. State is nothing but, I mean, I've just put it together in a tuple. Let's just assume. And I'm going to be stacking them together and I'm updating the hidden state with that. So torch.stack h comma input, and it's always important to mention which dimension, because by default it will concatenate among the batch, but the batch remains the same. You don't want to concatenate the batches, you want to concatenate like what's inside those batches, a stack, sorry. And then let's actually update our forget gate. Forget gate is nothing but torch.sigmoid self dot input sorry input gate h, sorry, this will be forget gate. Sorry, this will be forget gate. Forget gate, right? This will be used to multiply with the current c, which comes in the state as well. So c is equal to c star forget. This will be a value between 0 and 1. That basically tells which information to retain, which to forget. Input equal to torch.sigmoid self.input gate h cell information, which is the third tanh one, is torch.tanh self.cell gate h right. Right. Cell gate is nothing but a tanh function. And then they're added up, sorry, they first multiplied together. So, and then that is added up to C. So this C will now be updated as C plus is equal to input dot cell, input star cell, I mean, these two information. That becomes a new output. And now output, which is this fourth sigmoid thing over here, is nothing but torch.sigmoid self.output gate h, right? And then finally, h is equal to out star torch.tanh c. This is basically this small thing over here. You have to multiply that thing. Anyways, I'm going to be returning h, which is what input to the next layer, as well as the state, which is h comma c. So this is what I'm going to get. Anyways, uh, let's actually learn this. Sorry, invalid syntax. Sorry, or C plus actually just to avoid confusion. So learn. Let's actually just run this model. Learner, DLs, um, STM cell. Let's run this. Let's run this. What did I pass in? It just contains NI and NH. All right. So this is the LSTM cell. What I can do is that I can take in this. What do you call this entire RNN function and replace this self dot RNN over here with this self dot LSTM. And since it's not working, there is some bug. I'll make sure of doing that. But now, so what do you see that now it will actually not face that vanishing gradient problem and it will actually perform better. So that exactly is how LSTMs work. We've implemented LSTMs. Next time we'll actually look at transformers and all. I think I'll stop at this point. I think it's time. Quick thing before you guys leave. What you all should do, it's actually a very heavy lab as such. Quite concepts are quite heavy. So I recommend that you actually go through this once, twice if you have to, and look at each concept, specifically the APIs as well as like what exactly are we doing, how RNNs are built, how LSTMs are built, why did we actually need LSTMs in place of the traditional RNN, and go ahead and so forth. Also, you see that this is how simple it is to actually implement an entire paper, which is like one of the most revolutionary papers in NLP. So that's quite good. And your next lab is actually going to be next Saturday itself because we actually had to skip a class last time on 6th of November. So next week we're actually going to be see like how to actually train this and go ahead with transformers and actually do different tasks. So we actually only saw one kind of task. We'll actually see how to do different tasks like classification and like different sorts of NLP tasks. So it's a very good introduction to NLP. But again, if you want to catch up, if you want to stay, if you want to understand this concept well, you'll have to go through it once or twice more. So on that point, I'll stop this lab session and we'll continue next time. All the best, guys, and see you guys next week.